Hi, my name is Josh Benabou, and I'd like to tell you about our paper, Heterotic String Theory Suggests a QCD Axion near 0.5 nanoelectronvolts. This is work with my collaborators at Berkeley, Giulio Dainelli and Benjamin Safdi, and with my collaborator at CERN, Mario Reig. In our paper, we study the QCD Axion mass in weakly coupled heterotic string theory. In this theory, axions arise from dimensional reduction of higher form gauge fields, in particular, the two-form field Kalbromont field B2 and its 10-dimensional dual B6. The model-independent axion arises from the dimensional reduction of B6, and its decay constant is set by the fine structure constant alpha gut. For phenomenologically motivated values of alpha gut, for example, for alpha gut inverse between 25 and 40, the model-independent axion mass is restricted to a narrow range between 5.2 and 8.3 times 10 to the minus 10 electronvolts. Model-dependent axions arise from reduction of the two-form field B2 on holomorphic two cycles of the extra-dimensional space. The QCD axion in this theory is then the linear combination of the model-independent and the model-dependent axions. Consequently, its decay constant satisfies a quadratic sum rule whereby it is related to the decay constant of the model-independent axion, as well as to the decay constants of and anomaly coefficients of model-dependent axions. Consequently, we have that the QCD axion mass is bounded from below by the model-independent mass. On the other hand, obtaining model-dependent axions with masses which are sufficiently light such that these axions mix appreciably with the model-independent axion and allow the QCD axion mass to deviate from the minimal model-independent value requires special geometric conditions. Indeed, these model-dependent axions acquire masses from worldsheet instanton potentials, which are exponentially suppressed in the volume of curves. As we discuss in our paper, the overall volume of the compactified space is already small in units of string length, so the curve volumes are also typically small in the absence of special geometric conditions. In particular, for a Calabi-Yau threefold, as we study in our work, this would correspond to cancellations between terms in the volume form. To verify this, we perform an exhaustive scan of the Kähler moduli space of Kreuzer-Skarke compactifications on Calabi-Yau threefolds with up to 8 axions. We also study an ensemble of complete intersection Calabi-Yau manifolds. In summary, out of a few thousand or so manifolds that we determine are consistent with heterotic string theory, we only find a handful which have sufficiently light model-dependent axions to allow the QCD axion mass to deviate from the minimal model-independent value. As we discuss in our paper, Euclidean NS5 brane instantons contribute to the potential of the axion and shift theta bar slightly from 0. And future neutron electric dipole moment measurements of theta bar may actually detect a signal for most of the SUSY motivated parameter space. We also study in our paper the population of heavy axions arising in heterotic axiverses, and we show that these heavy axions generically decay before Big Bang nucleosynthesis and can also accommodate leptogenesis, unlike in Type IIB constructions. This is interesting because, for example, in heterotic E8 cross E8, the E8 cross E8 breaks to the GUT gauge group, which can include SO10, which, for example, in the 16 spinor representation can accommodate a heavy right-handed neutrino that can give rise to thermal leptogenesis. In summary, in our paper, we place a lower bound on the QCD axion mass in weakly coupled heterotic string theory of around 0.5 nanoelectronvolts. And as we discuss, we expect that this also applies to type 1 and heterotic M theory. On the other hand, in other areas of the string landscape, in particular in type 2b, F theory, and also M theory on G2 manifolds, the gauge groups, the gauge fields are hosted on local cycles, and the gauge coupling is determined by the volume of a local cycle, whereas the overall volume of the manifold can be much larger than this inverse gauge coupling. And this allows for a broad distribution of axion masses, including masses which are below our lower bound of 0.5 nanoelectronvolt for heterotic string theory. We also discuss in our paper why the cosmological moduli problem is simplified in heterotic relative to type IIB. Thank you for listening, and we hope that you'll check out the paper.